Hey, good morning, everyone. We'll talk about the exam later in the week, so not today, because we still have a couple of people to take the exam on the video side. But time-wise, how was the exam? Okay. Okay. Yes. Oh yeah, yeah. I we'll talk about that on Wednesday. Yeah, yeah. Sorry. Will be released by Wednesday. Yeah, I'm going through every exam by myself. So. Okay, so today we'll get started on GMMs, but before I do that, I want to kind of summarize K-means, and then it all will be in kind of handwritten notes. And today will be as mathy as we will get in this course. So there's quite a bit of math today. That's how I will just use my tablet for that. And then on Wednesday, I will come back to the formulas that we derived today, and then just kind of go through them just to understand what's really happening in that regard. Okay, let's start with the K-means. And the reason I'm really doing this on not slide, just so I can be very slow, because I think I really want to understand GMM, because they will be, to me, GMM and HMMs are really very, very important to know if you are do machine learning in your career. Okay, so let's really start with, I have a specific example in this case where I have two clusters. And then these two clusters are, I just want to label them as cluster square and a cluster a circle, right? And the features space, so p equal to 1, that means my xi's belong to R1. Okay, so I can really plot this on my one-dimensional axis, right? And I could do something like, these are the squares, these are the samples I have in this case, and then I have something like that for my other samples, right? So I have two clusters. These are the samples, right? So if you remember in K-means, what was the first step, right? So you have to choose K. In this case, kind of we are given K is equal to 2, and the next one is the initialization. And in that case, what we are initializing are the centroid. So this is centroid for one class, and the other one for the other class, right? Since we have iterative process, I will label basically this is iteration 0. This is the initialization part, right? So this is m naught and then m square at step 0. And then the next step is to really compute distances. So we could really use L2. So I have for every xi, how far it is from the centroid for the first cluster. I calculate the distance, and then xi from the second centroid for the second cluster, right? So that's basically, I do that for all I, right? I have n of these samples, right? And then what will be the fourth step? Will be the assignments, right? But basically now I say my cluster for the first one, right? And then I want to keep this iteration, right? So this is basically my cluster for the first, like for O, right? This will be equal to the sets of all xi's, right? Where the distance between xi and the centroid for that cluster is less than, I could really make this equal as well, xi and the second centroid for the second cluster, right? So this becomes my set in this case, right? I could do the same thing. Again, this is iteration 0. For the second cluster, all the xi's is vice versa. So I have xi minus the centroid for this cluster less than the distance for every xi from the second centroid, right? That's basically my assignment. Any questions so far about k-means? Yes.
That recent last step, we're just trying to group them together, right? They're just finding which ones.
Yeah, so this is just an assignment, right? So this is basically a cluster or a group, right? For those samples. Right. That's what I'm clustering. And this is the second cluster. So they have only 2 clusters for the square. Right. So now what will be the next step after this? Let me introduce some auxiliary function here before I continue. So let's really define zi square. This will be equal to 1 if the sample belong to cluster square cluster and 0 if it's not. And the same thing, zi circle or disk 1 if xi belong to the cluster circle and 0 if not. And this will be handy in a minute. Okay, so what will be the next step after this? Yes. Exactly. So the next step is, because now we have different cluster than initialization. So the next step is to recompute the centroid. So in this case, I'll have m not m square, and then now this is the next iteration. So I have 1, and this will be equal to the sum of all our xi's, where I clear this up a little bit. The sum of I equal to 1 to n of all the xi's, and then I'm dividing this by the length of our cluster at iteration 0, right? It's the length of this set, right? And then here, basically, we are assuming xi, it belongs to this cluster, right? Same thing in here, the summation over all samples that belong to this second cluster divided by the length of the second cluster at iteration 0, right? Any questions so far? Okay. Yes.
So were the centroids originally just random or?
Yes, so that's initialization. So basically, you just pick this initialization. You can pick from existing samples.
Literally just any data point?
Yeah. So basically, I could really just come in here and say, okay, I want to pick this one to be my m, like this could be my m square 0, and then this one here, just randomly, right? This is m disk 0, right? Okay. So basically, that's kind of, and now we are making assignments, right? I mean, and this assignments could be things like, okay, this is closer to this one, this is closer to this one, so this belongs to this cluster, and now you see this one belongs to this cluster, this one belongs to this cluster, or this one, right? It depends on the distance. This one obviously belongs to this one belongs to that one, and so on, right? And now, if you have these ones belong to this cluster in here, then you can imagine the centroid, this will move, depends on how the distance is, will move either right or left, right? And now you have different assignments and so on, right?
Does the centroid always make the same data point?
No, only the initialization. Only the initialization. After that, it will become any point in that space. Yes. It could easily, just as an example, I could just say basically this becomes my m at iteration 3, right? I mean, that could be the case. This one here, maybe this one here will be m circle at iteration 3, right? Just you know, these are valid centroid values, right? I could really recalculate this condition here, these equations to be something like this. And I don't really want to use this condition here. I want to incorporate that into my equation. So what I could do, I could really say this is equal to sum of I equal to 1 to n, and then I have zi naught times xi, right? Because zi naught will, or zi circle will be only 1 if xi belong to the circle cluster. Otherwise, it will be a 0, right? So I'm averaging over all of those, and then divide by the length of that, right? Similarly, I could do m square at iteration 1. Oh, this is the numerator. Summation over I between 1 and n. Oh, I forgot to say we still have our n sample, capital N sample, the total data, right? So this is squared times xi divided by the length. The difference between what I'm having in here, what I have in here, I really don't want to have this condition here. So I have this auxiliary function in here, right? This auxiliary quantity. So it will be easier to program or code or the algorithm. Any question? Okay. This is easier basically in here. Basically now I have another vector zi naught. Basically it will be the same length as our xi's, right? Now it will be ones or zeros, right? It will be a 1 if xi belong to the circle set, and it will be a 0 otherwise. This way I just have a vector multiplication like a 1 by 1, right? Point by point. So it will be easier to program it, right? It will be easier. No, but this one here you'll have to have kind of an if statement, right? If xi belongs to this one, right? It doesn't. No, it requires it because already this the information here, right? This has the information about the subset of xi's that belong to this set. It already has that. So now you have a vector xi, vector zi, same length, right? You just multiply basically 1 by 1, right? It just basically just it will save you computation. That's it, right? That's all what it will do. Is this we are not changing the calculation because we will use this in the GMM later on. Okay, so now let's restart with I have I think 3 scenarios before I get to the really the core of the GMM math. So let's start with this is the Gaussian mixture model, right? Let's start with first case. And the difference between the cases, what we are really given. Again, we have p equal to 1. That means all my xi's belong to R1, right? And then let's use the same data that I had before. Right? And now what we are given will be the difference between this case and the next. So case 1, we are given a lot of things. Case 2 will be fewer things. Case 3 will be fewer things, and so on until we get to understanding what GMM is all about, right? So the first one, what we are really given is we were told that we have 2 clusters. So K is defined. We were told that we are given actually 2 sets of samples, right? Their values. We are given that they are coming from two Gaussian distributions. Right? And then the third one, the membership, right? So we know which sample belong to which. So which sample is coming from where, right? And now what we need to do is to model our Gaussians. Okay. So now if you look at this, what we're really doing, right? What is really Gaussian mixture? we're saying this one-dimensional data set is really coming from a Gaussian distribution, right? So this is one sample or one Gaussian, and the other one is this Gaussian, right? So now if you look carefully about each one of those, I have, this is the mu, right? So I call this mu square. This is the mu, this, right? And then also I have the sigma for this sample, and I have the sigma for the square, right? So once you define this Gaussian, once you know the mu value and the sigma values, then you define basically where these Gaussians are, right? And now, if you notice in here, in k-means, we assign basically one or zeros. Basically, there is what we call hard clustering, right? So every sample, either it belongs to this set or the other set. So one or zeros. In here, just by looking at this Gaussian, what do you notice? I have a membership, right? I could really have a membership in here where I'm looking at this sample in here, for example. It has membership to this Gaussian and it has a membership to this Gaussian, right? So now I have a soft, basically, clustering, right? I don't really have hard clustering. So now I have a membership value that's between 0 and 1. Is a continuous variable, right? And now we are trying to figure out, does it really belong to this one or that one more, right? Which one is more than the other? You see the difference between the two? This is clear? Okay. So now for this case, we are given everything, right? All what we need to do is just basically to find the values. We are given this, we are given the samples. We are being told this sample belongs to this Gaussian or this cluster. All what we need to do is just find out the two Gaussians, right? So we need to find out the values for the first one, the mu naught, right? And then the sigma, right? So what will be the mu naught in this case? So I have summation over all my samples, n of them, right? And then I have the xi, right? If I do this zi circle, and then here is the length of the set, right? This is the set, the length of it. If I do this, then that's what means what? The zi ones are ones or zeros, right? This is k-mean, right? But now in here we have a membership, right? So now I need to introduce this membership. I'll call it gamma, which is a function of this zi, right? So now this gamma in here is really telling me how much of this belongs to this Gaussian, the circle Gaussian, right? And how much of it belongs to the other Gaussian. Same thing in the sigma square. You will have summation over all i's. I have the gamma of zi square. I have the xi, and then I have the length of, no, sorry, this is still, I have xi minus mu, and then square, right? This is the variance. Question? Yes.
So the gamma CIO just gives like how much inside that.
Yeah, for example, in this case will be like 0.7 for the circular one, and then 0.3 for the square one, right? So it's not 0 and 1 anymore. It's a membership.
It's not exactly 1 or 0.
It's not, yes, absolutely. It could be 1 or zeros, but it's not necessarily 1 and zeros like in k means.
Yeah, yeah. It's not like
Exactly. Yeah. And then it will be like the length of it will be depends on how many clusters you have, right? It will be a function of the k, right? And you can do the same thing. Similarly, you can really calculate the mu value for the other one and the sigma square for the other one, right? And now basically you have your Gaussian model, right? And now you have basically everything that you need to this GMM, right? Yes.
So is the standard deviation telling us how tightly compact?
Exactly. Absolutely. So I can go back here. I could say, let's look at the green one, right? I could really, if sigma is smaller, then this will be basically something like that, right? So this one basically will be less dominating than this one, right? And they are much tighter, right? And so the shape of it, and we'll see in a two-dimensional case like case 3, it will be much more obvious the difference. But in here, you can see it's much more centered to the right of this x-axis, right? So it will be on the right because where it is, the more you move to the left, most likely you belong to the second Gaussian, right? So because second Gaussian is much more dominating because the width is much higher. Yes, absolutely. So you will see basically a lot of these values in here. This one, if that's the case, then this one here, it will belong to that one, right? To the other one, most likely, right? Because that is very, very tight. Yeah. So that's really kind of a very easy case, right? Case one. Yeah. Yes. So now look at case two. And now what are we given? Same example as before. We are given mu square variance for the first cluster, the mean value for the second cluster, and the variance for the second cluster, right? Also, we are given, so this is one thing, we are given the number of samples in each cluster. Right. Now, what we are not given the membership. Right? All what we are given is basically this is the mu values for, and this is the two Gaussians, right? And basically how many samples in each cluster, but we are not told which sample belongs to which cluster, right? So that's the only thing that's different between case two and case one, right? So now we need to bring in how can we calculate the membership, right? So now what we need to do to model our GMM, we need the following quantity. We need to do that for every sample. And you can guess that. Basically, this is the membership calculations, right? So what we are looking at, we're looking at the probability, for example, for the square cluster or for xi, right? So now what's the probability that we have an observation xi, right? And it really belongs to our cluster, basically square cluster, right? And now we go to our friend, we use what? As before, right? We use the Bayes rule, right? The Bayes formula. So this will be equal to the probability of xi. That basically means we have this cluster, and then xi belongs to it, times the probability of our cluster. And then now I have, at the bottom, I have the denominator, I have to have probability of xi. What's the probability of xi? It will be the probability of xi belonging to this cluster times the probability of this cluster plus the probability of xi belonging to the other cluster times the probability of that cluster, right? So this is basically nothing but the Bayes formula, right? Questions? Well, so these are on the left-hand side, we have the posterior probabilities, right? So we have on the left-hand side, we have the posterior probabilities. Now let's look at this carefully, one by one, right? If you look at the first quantity, this one here, what is that? What is this distribution here? So that's basically that I have basically is probability of A given B, right? So that's basically I have my cluster, my Gaussian, and the next I belong to that Gaussian, right? So this is nothing but really the Gaussian distribution, which is 1 over square root of 2 pi. I have the sigma for that cluster, sigma square, exponential negative. I have the xi that I'm looking at, minus the mean for that cluster, square, over 2 sigma square. You see that? Right? That's our Gaussian distribution for that cluster, right? And now, what about this one here? What's the probability of this cluster? Where does this come from? Look at what we are given. I have the number of samples in each cluster, right? So I can really, from the total number of samples, I can really calculate what is the probability of that cluster, right? I have basically 30% of them are square samples, right? Something like that. So this one is really coming from here. Right? So I refer to this one from now on as pi. So this is pi sub square. Right? And this one here is our prior probabilities, which is the Gaussian distribution. Any questions? So now this one here is pi square. This one here is pi 1 circle, right? Now what I have on the left-hand side in here is our gammas that I had before. Remember our gammas were a function of the ZIs, right? These are our memberships. And that's exactly what we're calculating in here, because I have this quantity, and at the same time, I need to calculate exactly the same fashion, the probability of this given xi, right? I have to do the same thing. So now I have two gammas, right? I have these two gammas in here that I need to look at. But now this gamma in here is for sample I. I'm looking at the square cluster. This is for sample I, but I'm looking at this cluster. You see that? The difference between them? Yes. That was I used in case one, right? So in case one, I just verbally said plain English, what it is this nothing but the membership, right? How much member? But now we are calculating it is nothing but the posterior probabilities, right? That will give you the membership, right? That's the same one. It's the same gamma. Yes. Exactly, because in previously we were told basically what the memberships are. And here we were not told the membership. So I need to find this membership. I need to find this gamma, right? Before we were given that, right? Now in case two, we are not given that. So I need to calculate these posterior probabilities. Any question about this? This is extremely important. So it's really very important to understand what the ZIs are, what the gammas are, and then the pi, right? So I'm producing these quantities because they will be very important in with the GMM calculations later on. Any questions? Okay. So now, just to test yourself, what will be the expression here? What will I write here? Probability of what? Sorry, yes, circle, thank you. Probability of circle. Circle, right? And then, thank you. Right? And now that will give me gamma I circle, right? Now I have two quantities. For sample xi, right? One sample, right? The first one, probability of the square. The posterior probability that xi belongs to the square. And the second one, the probability that xi belongs to the circle, right? So I have two numbers now, right? Now I need basically to assign which cluster it belongs to, right? I just look at which one is bigger than that. So basically now, but basically how you cluster I or you assign I xi. Any question about this calculation so far? I'm moving very the story, just hopefully terminology will be easier. Yes. In this case, because we were already given, remember, we are given basically the memberships, right? We already have the memberships in here, right? So basically, it's already I have how much of this one belongs to this cluster or not, right? If it's given to me like it's absolutely just like the k-means, like this gamma basically in this cluster, absolutely just one, and the other one is zero, then it's just one and zeros, right? Or I'm giving 80% belong to this cluster, 20% to the other cluster. That's given to us in case one. Yes, we are not calculating it. Yes, the membership is given to us. That's why basically I have in here as a given, right? So all what I need to find is construct the Gaussian, right? Percentage. That's the membership. Exactly. Back to what we were talking about before. It's a soft clustering, right? So it will be say 80% in cluster 1 and 20% in second cluster, for example, right? Something like that, right? But now, yeah, but I'm just simplifying here. This case 1 is like a kindergarten clustering, right? Say basically in this one here, we're giving everything now. All what you need to do, you just basically when the Gaussian has two parameters, the mean value and the standard deviation. How can we calculate the mean value and standard deviation? Just all what we're doing in case 1, right? Now in case 2, we're making a little bit harder, which is basically now I'm giving you what the mean values for these Gaussians and the sigmas for the Gaussians, but now I'm asking you to give me the membership. So it's the other way around, right?
I'm trying to think of the situation where I always thought of thinking as being like you have a bunch of data and
Yep.
you're trying to put it together, but in this situation, you're trying to do that and you're also given.
Yeah, this is case 1, case 2, and also case 3. All of them just to introduce the theory, right? But in reality, case 3 is really what happens. You have samples, and now you are told cluster them. So it's unsupervised, right? So that's one thing. And you don't know how many clusters. You need to experiment with different K, right? So basically, it's completely unsupervised, right? So that's why every time, if you look at the K means, the first step was choose K, right? So basically, you type, and as we said last time, you pick K equal to 2, and then see how the clustering looks like. Go back, change K to 3 or 4, and then look how the clustering, and then how you can pick that. That's how you pick K, right? So it's clustering is completely unsupervised, right? We're just building the case for the different terminology. And so now, in this case, we are introducing the calculations of the posterior probability, right? This is very, very important. Any question about this step? Because it's very essential for the following few steps. Any question? Yes. Say? Uh-huh. No. So that's the actually and here this is the length, right? This is the length of it, right? Because I'm averaging, right? That's the length of cluster. It's not C0, it's C circle and C square, right? Yeah. That's the length of it, right? Okay, so now let's go to next case, and we are just generalizing it a little bit, okay? So case 3 is really closer to case 4. Case 4 is our final case. Now, what we are given, again, it's the same as before, same samples, but now what we are given information is different, right? Well, what we are told, P equal to 1, Xi equal to R1. Then we were told the samples, the data. But now the only difference between what I said about clustering is basically we're told the number of clusters. Somebody told us what K is. The difference between this case and the previous case we were given mu, we were giving sigmas, right? Now we're not giving that. We're only given the samples, what they are, like just data, and we were given K, the number of clusters that we have, right? That's all what we are given. And now what we need to figure out is basically, again, let me just do this quickly. So I have not exactly the same data every time, but close enough. And now what we need to start to have an algorithm, right? So what will be the first thing? I mean, I want to use Gaussian mixture model, and you will see basically in the homework why Gaussian mixture model are really much more powerful than K-means, right? And you will see that, and we'll talk in more detail on Wednesday the difference between the two. But now, if I want to use Gaussian mixture model, what will be the first thing we need to figure out? What's that? Exactly. We need to figure out what the Gaussian. We need to initialize. We need to start with some Gaussian, right? I could really just start by saying, I want to have one Gaussian here, right? Why not? And then another Gaussian here, right? I have no information about right? That's initialization, right? And then I'm hoping with time with different iterations, as I'm improving my algorithm, this one here will move here, right? And this one will move somewhere here, right? That's what we're trying to do, right? Not only they are moving, that means the mean value will change, but also the sigma will change, how wide and how narrow they are, right? That's all what we are really trying to do, right? We are trying to converge basically over number of iterations. Could be 10, could be 100, it could be 1000, right? But all what they're trying to figure out where the mean value on this x-axis, because we have my feature space of length 1, right? So dimension 1. So I have x-axis only. So I need to find where the mean values are and how narrow and how wide basically these Gaussians are. That's all what I'm trying to do, right? So now we start with the first step. Call step 0 because it's already given. So k is given to us. As k equal to a 2. Then that will help us to do initialization. So now, what are the initializations? I need to find mu for the square, the sigma for the square, the mu for the circle, and the sigma for the circle, right? But now I need to bring this iteration element. So this is iteration 0, 0, 0, right? Okay, that's the first thing. Now I have the mu, I have the sigma, right? Then if I do that, then I have case 2, right? Then I have case, remember case 2? Case 2, we are giving these mu values. Then now I know what to do. I need to calculate the gammas, right? Which is nothing but the posterior probabilities or the posteriors for our sample, right? So now the next step is to find or determine or calculate the probability that my xi belong to this sample, this cluster, sorry, and then circle xi, right? And then I need to do that for all where I between 1 and n, right? Now this step, just remember it for now. We'll revisit this in a few minutes. We call it the E step. Okay, just put it on the side for now, and then we'll come back to this one. Once now I have my posterior probabilities, right? Now I have some membership vectors for every single sample, right? So what do I do next? So now remember, I have the membership, like for each sample, it belongs with this much to this cluster and with this much to the other cluster, right? But we have to make an assignment about clustering, right? So the higher value where that cluster, basically where that sample belongs, right? So now I have a new clustering, right? What do I do next? Once I have new clustering, I need to recalculate again the values for mu sigmas for both of the clusters, right? So now then the second step is to adjust and recalculate the values for mu, sigma, mu, and sigma. Oh, sigma. But now these new calculations will be for the next iteration, right? I have an update now, right? I keep repeating that until I have a criteria to stop, right? So this one here, we refer to it as the M maximization step. And we'll revisit this, these two things in a few minutes. Are we clear on the algorithm in here? Are we clear on these steps? Okay. Okay. So let's look into the details of these steps. Okay. So for the first step number 1, when you look at the priors, which is probability of xi for cluster O, for example, I have 1 over square root of 2 pi. I have the sigma at that iteration, and then I have exponential xi minus mu circle divided by the 2 sigma square, or this square here. So, okay. And then from this prior, I can calculate the posterior probabilities, xi, the square, probability of the square, right? We agree this one equal to what? Gamma I, O, right? And now basically I have, or compare gamma I, O, and gamma I square, and then you make the assignments. Okay. And the second step, we have these calculations. The mu naught is 1 over all my samples in the circle. And I have the summation over all my samples, I between 1 and n. I have my xi's, but now I need to do this, right? You see that? That's the gamma, right? Or, since I have new notations now, so I have n circle, summation over all I between 1 and n. I have gamma I circle xi, right? The weighted average of all my samples in cluster O, right? This is the weighted average, right? So this is of all samples in this cluster. And the same thing for the sigma O, 1 over n now. I have n circle, sorry, sigma between 1, I between 1 and n. I have xi minus mu circle square times my gammas I circle, right? And hopefully now the Gaussian is already moving into the right direction and so on. Do you see that? And now I have to do this for every single iteration. So I could really go back in here in this detail and say, this is basically sigma at 0. This is mu at 0. This is sigma at iteration 0. And basically these are my gammas at this assignment. And now this is the new calculation at the next iteration. This is the new one at the next iteration and so on, right? And this is gamma at 0, and this is gamma at iteration 0, right? See that? And then now I have an algorithm. I just keep going to the for loop. Yes. So you keep doing that until you have a criteria to stop, right? And there are tons of different criteria. You can imagine that one, as we did like in the k-means, like what is the total cost of our clustering? Basically, the distances from all the centroid to the samples in the cluster. That's the total cost, right? You could do something very similar here, but since you have an iterative process, then we could do how much my assignment change, how much my membership vectors change, right? So you have a number of things to decide upon when to stop, right? But as there's no one way, right? It depends on what your criteria is. And you could say, I have an epsilon, and then if the change is below epsilon between one iteration and the next iteration for my mean values and the sigma values, then I will just basically stop, right? That could be one. Or you can just look at it in the assignment side of things. So it's up to you to find the criteria. Okay. Yes.
So is this algorithm different? Is that the initialization is random?
So eventually you get to the if your initialization, as we said in the k-means, right? When you have the initialization, basically where you start, it becomes an issue, right? There's a very similar problem here, but actually it will take you longer to get to the correct answer. But eventually, once you get there, because remember, we are looking at the Gaussians, like the mean values and their width and breadth, right? As you move into the right place, they will converge basically to very close to each other, like almost the same solution eventually. But it will take you much longer. Exactly. Eventually you go there. And then you will see in the homework, for example, we generate data for you where the two samples cross each other in a two-dimensional space, right? But the samples in the middle, they're already coming from a certain Gaussian. The k-means will just completely get this wrong, right? But the Gaussian will really figure that out in a very, very nice way. It will take a little bit longer though. So, but it's very powerful in that sense. Now let's really look at case number 4, which is basically the generalization for everything that we have looked at. So now what we introduced, basically the posterior probabilities, you can really calculate these using the Bayes formula, right? We introduced the quantities like the gamma, which is the membership, right? For every sample. Oh, 4, thank you. Yeah, this is 4. So the gammas, which is every sample you have a gamma, which is basically how much membership in each one of the clusters. We have the pi, basically the probability of each one of the clusters, right? The pi values. We have the zi's, which basically tell you if for a sample I is equal to 1 if it belongs to that cluster and 0 if not, right? For every single cluster that you have there. So let's look at this case. Now we just make it a little bit, although I'm having k larger than 2, right? I don't know. So basically, xi's belong to a general feature, basically where p, right? So now we have more than 2 clusters, right? And we have p features. This is the general case, right? Which you will be dealing with. Let me illustrate basically the case where I have k equal to 2 and p equal to a 2, right? So imagine I'm looking at certain animals and I'm looking at the 2 features. One feature is the size, and then here the speed, right? And then somebody told me basically I have the horse basically samples. These are squares. And then I have, I don't know, turtle. So obviously, basically for the turtle is small in size and slow in speed, right? But for the horse, is large in size. So I have 2 features, right? But now what the Gaussians are really telling us in this case, if you really try to draw this around it and draw something around this cluster here, right? So I have this Gaussians now. You see the Gaussian mixture. I have a 2-dimensional Gaussian, and basically the first one on the blue is giving me this kind of a circular shape, right? That's one 2-dimensional Gaussian, right? The second 2-dimensional Gaussian is giving this oval shape. You see the oval shape in the red, right? So now that's basically now you have your mu values. Your mu values now. Your mu is not a single value as we had before, right? Because the p now is larger than 1. So in this specific case, the p is equal to what? 2. So the mu in here, right? The mu value is what? Is a vector of length 2. Understand that? This is the general Gaussian mixture model. So, and that's basically the reason where I tried really kind of to go very slowly into this. So the xi, look at the xi, I have 2 features. I have the size and I have the speed. Similarly, I have the mu, right? It will be a vector now, same as xi. And this will be some quantity in here, which is the mu value in the size side and the mu in the speed direction. And the same thing for mu circle. It will be 2 quantities, and so on, right? Do you see that? So imagine basically that I have mu not will be something here, and then the mu other one will be somewhere here, right? This will be the mu. But each one of them, they have what? They have, this is the first element, and this is the second element. They have 2 values, one in the size and one in the speed. You see that? That's where a lot of confusion happens in GMM when you go to p equal to 10 or 50 or 20. Are we clear on this? Okay, so let's now look into the following. So now I have these mean values. Now, before, remember when I told you the Gaussian, basically I have the mean value that will move me. If I have one-dimensional data, I'm moving on the x-axis, so it'll give me the mu values. And then I look at the sigma, it tells me basically how wide and how narrow it is, right? But now I'm looking at this, the mean value will tell me basically I'm here in this dimensional space, or I'm here in this two-dimensional space. That's the mu, right? But now I have one of them is giving me a circular shape, the other one is an oval shape, right? How can I describe that? I don't have sigmas anymore. What do I have? The what? Exactly. So now I have the covariance matrix that we introduced 2 lectures ago. I have the covariance matrix, right? And the notation basically, in this case, will be a 2-dimensional, a 2x2 matrix, right? This will give me the shape of my circle. Is it like a perfect circle, like in this case, right? Oops. Like this one, or an oval. That will give me the shape of the 2-dimensional Gaussian in this case. Okay. Any question? Is the realization a little bit clearer? Yes.
The mean value is that matrix for one value for each.
Yes.
Is that the same thing as a centroid?
Is not like centroid is basically how far you are, like you are averaging, right? The L2 norm of all the data, right? This one here is telling you where basically the Gaussian center, the peak, is located. Not necessarily, basically it depends on where the data, where how far they are.
Okay, so the Gaussian center, the your centroid are not the same.
Not the same thing, yes. But in here, if you look at the second, it will be obvious from in the blue one, maybe they are the same, right? But in the other one, it's not necessarily the same, because you'll have this, you have in the covariance, you have 2 kind of segments, right? So you have one along the negative 45-degree line is much wider. The perpendicular one to it is much narrower, right? So basically now, what is that the mean value of the sentence? Not right where that's located, right? So it's you have location of the mean and the location of the shape of the Gaussian will give you basically those Gaussian. Once you have the shape, and once you have these mu's, then you have basically all what you need for your Gaussian mixture model. Okay, so now given all of this, so now I have the general case, but I can do it for this specific case. I have k 2 or larger, right? And then xi belong to this RP. Now our job is to find the best values for what? Now we have the mu vector, right? We have the covariance matrix. What else? And the pi. Remember the pi? Right? Because if I have these things, then I can calculate the gammas, the membership, right? What is the pi? The pi, remember the probability of each one of the clusters, probability of the square, probability of the, right? If I have those, then I can really calculate everything I need. Let's go back to this one, right? If I have these, if I have the gammas, right? See that? If I have the pi, sorry, the pi, you have this pi, I have this pi, and I have the mean value, and I have the sigmas, then the gammas are calculated. You see that? Okay, so now we need to find the best values for our problem. Okay. And then we'll talk about what we mean by best, right? And the best value. And now, set to probability of xi is nothing but I have the pi thrown to the one cluster, and then, no, sorry, it should be a Gaussian, right? So it's a normal distribution. Of xi belong to a mu covariance matrix plus pi circle normal distribution xi mu for the second one. And that will give us the probability of the xi's in this case. Okay? Any questions? Okay, so now what will be the strategy? How do we do this? How can we find the best values? So we have everything that we need, but how can we find the best values? Any ideas? You have n of these samples, right? And you know basically that you need to find the Gaussian distribution, means the mean values as well as the sigmas, right, for each of the Gaussian, or the covariance matrix for each of the Gaussian, and then the pi, which is basically the probability of each cluster, right? Right. So, but you're gonna do that for every single sample, right? So that's basically the generalization case. We need to look at the probability of the matrix X for all samples. This basically has all samples. Remember this X, where we have this is basically n, and then here I have p features, and n by p matrix. Remember that? That's X matrix. So you have to find the probability of this X given our pi, mu, and the covariance, right? We need to find what will be the best value in this case. Okay, so we need to maximize this quantity, right? We need to find the best values in this case. Okay. Now, can we write this in a simpler form? How can we do this? We need to make assumptions. What is the assumption that we have been maintaining for the last few weeks? That these samples are coming from, yes, exactly, it's an IID, right? So basically these are independent of each other, right? So now that basically means this is the product over all i's between 1 and n of every individual sample. What every one of them? I have sum over k. Remember, k is the number of clusters, right? Large k, right? And for each one of them, I have pi sub j times normal distribution, where I have my xi given mu for I. Is it I? No, it should be j, right? It should be j. Yes, thank you. This should be j, and the covariance for cluster j, right? I need to do that basically repeatedly for every single cluster. I have k of them. If it's equal to 2, then I can, then if k equal to 2, then I have what? I have exactly what I have in here, right? And then I keep multiplying them with each other, okay? So now this one here, just for your observation, this one here, because we assume independence in this case, okay? Okay, before we do the optimization, let's look at some quantities. So Zi, and now I will introduce this as Zij equal to 1 if Xi belong to cluster J, right? And 0 if not. And the same thing, our gammas, Ij, is basically a function of the Zij's, right? Which is the probability that I have, you know, Zij is equal to a 1 given our Xi, right? It's our gamma. And we found the base rule for this one, probability of Xi belong to this cluster times the probability of that cluster Then I have probability of xi, dij. I sum over all k clusters, right? So I quickly simplify this. When I have the summation over j between 1 and capital K, right? I have probability of zij equal to 1, and probability of xi, dij equal to 1. And then here I have probability of zij equal to 1, times probability of xi, dij equal to 1, right? And now, what are the values? What is the quantity here? What do we call this one? This is what? This is our pi j, right? What about this quantity in here? This is pi j. What about this quantity in here? This is normal distribution, right? Where I have mu mu j and sigma or covariance j, right? And so on. Questions? Zij is just as an auxiliary quantity, like an intermediate quantity, is this one. Basically, because although we have a membership, right? But we need to make an assignment for the clustering, right? So the larger value for the posterior, we say, okay, it belongs to this cluster. This will tell us especially which assignment it belongs to which cluster, right? Although is a membership, right? Oh, this one should be, sorry, this one is not right. It's conditional, right? This is the normal distribution of xi given that. Same thing in here. So the same quantities, okay? And then, so I have one quantity in here. I have another quantity in here. So I have the z, I have the gammas. And then the last one I want to introduce is n sub k. This is the sum over I between 1 and n, and then the sum of all our gammas. Okay? I'm summing over all my gammas, right? For that particular sample. Okay? Oh, sorry, there's no j here, right? This is k. I'm doing that for that cluster k. Or we can just say n sub j, sum over all I between 1 and n, gammas I, j. Doesn't matter. It's just the cluster. For each cluster, I have the total number of total values of gammas. Okay? Because remember, there is a subset of those samples in cluster K or cluster J. Okay? Okay, are we done? Our job is still to maximize this quantity, right? Now we introduce these intermediate results, right? So now what do you need to do? You take the derivative, equate to a 0, right? Right? And then we have if k equal to 1 and p equal to 1, you can really get some closed form solutions. But if not, we will have iterative process. So we will not really go through the derivatives, but I'll just give you the take the derivative of probability of x given mu, pi, and the covariance matrix with respect basically the pi, the mu, and the covariance matrix, and equate to 0. Okay. What you will be given, we get the following. So we have mu for cluster K is equal to 1 over nk sum over I between 1 and n. I have the gammas times the xi. If it's easier for you, just like this makes it j. I mean, just like, because capital K can be confused. So this is j, right? This is j. Either j or small k, depends on what your notation is, right? The next quantity will be given is the covariance for j, 1 over nj, summation over all samples, and then I have the gamma ij. I have xi minus mu k or mu j times xi minus mu j transpose, right? Because all of these are vectors now. Then finally, I have my pi sub j, which is n sub j divided by n. These are the three quantities that I'm looking for. All right. Now, if you look carefully at each one of these quantities, what do I need? I need the gammas, right? I need the nj's, the nj's in here, the nj's in here. I need the gammas in here, right? Right. So each one of them, I will need basically. But now, if you look at the gammas and the nj's, the calculations in here, look at this. For the gammas, I need what? I need the pi, right? Correct? I need the mu's. I need the covariance, right? Same thing in here. For the nk, I need the gammas too, right? So now we have this kind of, they really depend on each other, right? And that's basically where we say, okay, now we need to do an iterative process, right? We have to have an initialization, right? Do some calculations and keep doing that iteratively until we get to a converged solution. See that? Any questions? So now, putting everything together, so what will be the algorithm, right? The first thing is you need to basically do initialization. What do you initialize? What do you initialize? The Gaussians, right? So we need to initialize our mu k, or call it mu j, mu j's, the covariance for each cluster, and the pi for each cluster. J is 1 to capital K, right? So J is basically an index for the cluster that you are dealing with, right? So now you do initialization. The next step is to do compute what? Once you have these values, what do you compute? You remember the three quantities that we, intermediate quantities, the gamma, right? The Zi, the gammas, and then the nk or the nj, right? Yes.
Pi from mu and the covariance. Why would you initialize pi?
No, pi is basically will tell you how many, you have to start with saying how many samples in each cluster, right? But you don't really have any values for gammas yet.
That's what we did in case 3.
Yeah, because we're given, right? This one here. Yeah, so exactly, but we have to start with this gammas, right? With this Gaussians, right? No, we at the very beginning, right? When you initialize, you have to say basically how many members that you have in each cluster, right? Initialize it, you don't have that information, so you have to initialize it. You don't assume anything, basically. So now what we have in here, don't confuse case 1, case 2, case 3. These are very special cases to introduce different quantities, right? In this case in here, or what you are given, right? In this algorithm in here, you have the samples, and then you are told what k is. But most of the time, you have to guess what k is. But for now, we assume that we are, we can guess what k is, right? But now, how do we start, right? So now you have quantities where, in our optimization, right, when we take the probability of all the matrix X, right, given the pi, the mu, and the covariance matrix, when you take derivative to 0, what will be the values? This will have these quantities, the pi, right, and we have the covariance, and then we have the mean, the mean values, right? So now, but these three values depend on the gamma, right? Depend on the nj or the nk and so on, right? So now we have this iterative process. So you have to start by the first step to say what do your Gaussian mixture is, right? And then that's basically what your initialization. Once you have a guess or you have some initialization, then you compute the gamma ij's, right? And now this computation here is based on what? So now based on what? When you do this calculations, right? You are really doing the expectation calculation. Remember the E step I mentioned before? This is the expectation step, right? And now once you have that value, then you do and recalculate the mu, the covariance, and the pi j. And this one in here is we call the maximization. And why is that? Because basically when I maximize this quantity, I get these expressions in here. So this is the maximization, this is my expectation. And that's why basically this algorithm in here, we call it the expectation maximization algorithm. Or the EM. You see it very, very well known in the literature, the expectation maximization. Because in one step, you are really doing the expectation based on your initial guess, or based on the previous iteration, the next calculation based on your optimization, and so on, right? Any questions? And then you keep repeating this. Until a convergence criterion is met, right? Until you meet a convergence criterion. Yes. Is K. Only the number of. No, yeah, no. It's the initialization basically is not the hyperparameter, but K is the hyperparameter. Not everyone, but hopefully it will, but not necessarily, because it depends, right, on your data, right? Yes, you keep until you converge, right? But there will be certain situations where it will be very, very tough to converge, right? Imagine that if you have your data basically are really very close to each other in that space, right? Right. So now if the two samples really kind of have the same membership, right? The 50-50 all the time from Gaussians, then your assignment might be wrong in that case, right? So in k-means, right? K-means if you have balanced data and you have reasonable distance between them, k-means will work very nicely, right? If you have imbalanced data, right? You have some samples are some cluster very, very few samples, the other one is much higher, right? K-means will not really work very well in that case. GMM will work very well in this case, right? So when you have this imbalance, basically the distances are not really uniform or are not really symmetric, then GMM will really work. But you still have to have some kind of differentiation between the samples in the feature space, right? So now in the homework you will have something like the two data, the two Gaussians are intersecting, right? They intersect now. Because you have a lot of samples are not in the intersection region, right? Your Gaussian will really build very nicely because you have quite a bit of samples outside this intersection. So it will figure out basically this belongs to this Gaussian or the other one, right? But that's a special case. What if you don't have that many there? And I think we have a variation at the problem where we reduce those variations, right? And now you have your data is in the intersection for one Gaussian. That's when the Gaussian start to kind of, be not really very good because it doesn't have any other information to tell you these should belong to that bigger Gaussian. So it starts become very confused about this samples in the intersection, right? So it's better than k-means, but there are cases where it fails for sure, or not fails, but it doesn't converge, right? To the correct solution. Okay, and we'll see that some examples next on Wednesday. And in your homework, also we have a very nice kind of exercise there. Any questions? Oh, yeah, of course, yeah. So, yeah, I have it in LaTeX, but I will upload this one here. So we'll do that. Okay. Thank you. We'll see you Wednesday.